Okay, well, thanks, and welcome to the second session of Economic Geology for Lunar and Asteroid Resources. The subject this week is mineral evolution. And thanks for joining us. Hopefully, our audiovisual system seems to be working better, at least from the start. So again, if you have comments, questions, statements, just put them in the chat box for the online audience. The students around the table, if they have a question or a comment, use the microphone because that is live right now and should work just fine. And we shall begin. So mineral evolution. The theme of this course, of course, is you're not in Kansas anymore. And back in 2008, Robert Hayes and his colleagues published what I thought was a insightful idea about the origin of minerals in the solar system. The idea is that mineralogy evolves on terrestrial planets and moons and asteroids, basically as a result of physical, chemical, and biological processes. And this evolution leads to a radiation of mineral species. And so when you have a planet or any physical object is basically a very large chemistry and physics experiment. And when you change the physical or chemical conditions, what you do is things react, and the output is more diversity in minerals. And so mineral evolution over time is a change in the diversity of mineral species, in the relative abundance of minerals, in the compositional ranges of minerals, because you can get more complex, rarer stuff stuffed into these minerals, and also a change in the grain sizes and morphologies. Now, before I begin, I'm going to actually make a few definitions. There are those that probably are not aware of what a mineral actually is. It is a crystalline compound with a fairly well-defined chemical composition, but a specific crystal structure. And it's the crystal structure that really makes a mineral. So, water is not a mineral. Water ice, however, is a mineral because it has a specific crystal structure. For evolution is generally associated with biology. And it's the process by which different kinds of living organisms are thought to have developed and diversified from earlier forms during the history of the Earth. A broader definition is that it's the gradual development of something from fairly simple forms to more complex forms. And what we're talking about is basically a form of radiation or diversification where minerals react to changing chemical and physical environments. And the results are a change to their fundamental crystal structure, along with their physical and chemical properties, because it's the crystal structure down at the quantum level which determines their physical and chemical properties. So, an example is olivine. Olivine is a very abundant mineral. It essentially makes up the mantles of the terrestrial planets. Phosphorite is a magnesium-rich end member. So it's magnesium with silicon and oxygen. If you add water and time, you get serpentine, which is magnesium, silicon, oxygen with hydroxide. Add high pressure, and the chemistry stays the same, but the crystal structure transforms and you get a thing called ringwoodite. You add more pressure and it decomposes into silicate perovskite. We quickly get into minerals that I can't pronounce very well. So you'll just have to forgive me for this. And ferropericlase, which I have no, why they call something that's magnesium rich ferro. I looked this up and yes, that's its actual name. You can get an iron form of this, but anyway, mineral names. Turns out, amazingly enough, that there's something like, there's there's something like 5,400 known minerals. But people keep track of the obsolete names of these minerals, and there's something like 35,000 obsolete mineral names. So this gets really complex really fast. So anyway, but to continue, the silica-rich igneous systems take olivine and react it to form orthopyroxene. If you heat olivine under reducing conditions, you get enstatite plus free oxygen and pure magnesium. So just one mineral, by changing the local chemistry, the pressure, the energy, you can evolve this into 6 more minerals. And actually, olivine evolves into lots more than that. So the mineral inventory of the solar system has gone from a few dozen minerals to something over 5,400. As of November, there are 5,417. And 3 processes drive this evolution. That's separation and concentration of chemical elements from their original uniform distribution. Greater ranges of temperature and pressure, along with the availability of volatiles. And then the generation of far from equilibrium conditions, usually by living systems. And if you look at Earth history, minerals have radiated and diversified hugely over Earth history. So for instance, the diversity of carbon minerals, which we take for granted, basically is a relic of Proterozoic times. There was not much diversity in carbon before 2.5 billion years ago. The evolution of manganese minerals is essentially directly associated with the supercontinent cycle and big mountain building episodes. And so you can read the supercontinent cycle really in the peaks of the abundance of these things, and also a progressive change in the oxidation, the oxidation state of these guys. So you can get more oxidized as you get more oxygen in the atmosphere. The GOE here is the Great Oxidation Event, which we will talk about. Basically had no beryllium minerals before 3 billion years ago. Concentration, thanks to plate tectonics and continental collision, allowed you to diversify the minerals that were based on beryllium. So Hazen and his colleagues proposed 10, well actually 11 stages of mineral evolution, going from a dozen mineral species in the pre-nebular era all the way up to the 5,400 we have today. When he wrote this, there was about 1,000 less, but people are adding new minerals all the time. Question, use the, no, you have to press the button. The button is in the front of it. Yeah. There we go. And the green light goes on and you know you can talk.
So besides from olivine, what were some other pre-nebular minerals?
Did I plant this question?
No.
No, oh, good. I feel much better about that because that's going to come up in just a few minutes. So anyway, almost all of this chart directly relates to the Earth and the chemical and physical and biological conditions essentially operating on Earth. So for our purposes, really the planetary line is the first 3. And so, and actually the asteroids are restricted to the first 2. So you can draw an asteroid line and really a lunar line on these things. And you just don't get any of this evolution for lunar asteroid resources below those blue and red lines. And we'll be coming back to this, but keep this in mind because essentially mineral evolution depends upon heat sources. And if you lose your heat sources early on, you stop evolving. And this is another chart from Hazen about mineral diversity. Time versus mineral diversity. And basically, all we're going to be talking about in this class is this little area occupied by the first red circle in the lower left. All the rest of this mineral diversity just really doesn't apply too much to us. So the first dozen grains. Now, we actually have a fair number of pre-solar grains. It's about 0.1% of the total mass of meteorites. And this is a pretty narrow collection. Nitrides, carbides, things that you don't see a lot, cohenite, titanium carbide, of course, diamond and graphite, some iron alloys, oxides, and silicates, and our old friend phosphorite. There's probably a lot more. The problem is that a lot of the pre-solar material is amorphous or only partially crystalline, and it's also tiny. And tiny things that are not very crystalline are hard to work with. And of course, here's a photomicrograph of a cosmic dust particle. This is what you get to work with. So, things that are 20 microns seem to be huge to you. It suggests that there's a lot more out there that we just don't know about yet, but that's something for the future. What happens is you take all this pre-solar material in these molecular clouds and you create a solar nebula. Solar nebula collapses under self-gravity. This is, I will blow off too many explanations of this because this is a multiple semesters long problem that I don't want to deal with. But suffice it to say that the collapse heats up the nebular material. The amount of the heating depends upon the location. If you're in the interior of a solar nebula toward the center, it gets really hot. The exterior doesn't get as hot. You have a thing called a frost line. And so inside the frost line, and you can see that in the lower image, inside the frost line, things are not icy. Outside the frost line, things are icy. The other thing that happened to our protoplanetary nebula is it got seeded by a nearby supernova, and a huge amount of short-lived radioisotopes got tossed in. The exact timing of when things got tossed in is subject to a great deal of debate, but suffice it to say they're there. The minerals that you get depend upon the materials that are available. And so what you build the nebula out of depends upon cosmic abundances. The pattern of cosmic abundances is driven fundamentally by nucleosynthesis. And you end up with a sawtooth pattern that happens to be of abundance, that happens to be a direct result of the nuclear physics of fusion and shoving things together in stellar furnaces. Question?
So I used to work in stellar astrophysics with supernovae, and
Yes.
particularly supernovae seeding different amounts of minerals in close, like, solar systems. Do you think, yes, do you think it would be reasonable to assume that there would be a good amount of variation and that would affect mineral evolution in different things, or is it going to be primarily nucleosynthesis?
Well, the short answer is absolutely. Because the number of times you go through these nucleosynthetic cycles tells you what the relative abundances of different elements are. The really big change in the last few years is I would cynically say that people that do this kind of nucleosynthetic
yeah, it's every
calculations
Monday.
have actually been kind of lying to us for decades. Because what happened was
Well,
that once
Dr. Dave
you
Crane's right there.
confirmed that you had neutron star collisions, then all the charts of where a lot of elements came from changed almost overnight, because really the calculations did not actually make enough abundances from just supernovas for various things. That's okay. It's not that's not my problem here, where these things come from. This is what we get in the solar system. And what we get in the solar system, especially for terrestrial planets, is illustrated by the whole Earth line there. About 2/3 of what we have is oxygen and iron, because those are way abundant. And you can see they're way abundant in the sawtooth diagram below. And the next down is silicon, magnesium, and then you get smaller and smaller amounts. There's still quite a bit of aluminum, for instance, and calcium. And you will see, if you look at all these mineral compositions that I throw up on the screen, that things like magnesium and calcium and aluminum show up all the time. So anyway, what you get depends on what's available. In different solar systems, question. Yeah.
Isabel wants to know, how do we know this happened? Can we still see the supernova today?
How do we know this happened? Well, it happened 4.5 billion years ago, so we can see the chemical traces of the supernova. In fact, there's evidence of chemical traces of multiple nearby supernovae. So it helps make for a rich nebula if you have more than one. It's a bad neighborhood to grow up in if you stick around. But luckily, we're no longer in that neighborhood, so it's okay. So anyway, you get off to stage one, which is accretion and formation of chondritic materials. So you've got the solar nebula. Materials get hot, they vaporize, they condense out of the cooling solar nebula, and you get high temperature minerals condensing first. These are the so-called calcium aluminum inclusions, the CAIs, and you basically get about 24 mineral phases. That's a CAI right there, the thing with the red arrow to it. And these are the first things those are the oldest things in the solar system. You get all these well-known minerals like spinels and melolites and perscovites. Turns out that there's a silicate perscovite and a calcium titanium perscovite. And I don't know who names these things. Hibonite, which the chemical variation on hibonite is just mind-bending. Anorthite, fosterite. How do we know about the formation of chondritic materials? We have 70,000 meteorite specimens. And there's a site called the Meteoritical Bulletin. And if you want to know excruciating detail on many of those 70,000 specimens, it's all there. Help yourself. And so what we do is make chondrules, because chondrules are what comprises chondrites. Cooling nebula produces more progressively lower temperature minerals, and chondrules dominate at this stage. Chondrules are basically the sedimentary sand of the solar system. They make up the chondrite meteorites, and they're these little, hard to see often, but easy to see if they're white, these little BBs of millimeter-sized stuff that are formed probably by flash melting in the solar nebula. How this actually works, nobody is sure. There's a number of different theories. I don't believe any of them, but I'm sure that sooner or later somebody will figure this out and everybody will agree. But right now there's not broad agreement. Chondrules they basically contain the diversity of the solar system. and you get a diversity of minerals, sulfides, oxides, phosphates, lots of things. So at this stage, the mineral assemblage is about 60 minerals. You get, what they do is they sample the diverse environments of the solar system. So you have a huge range in oxygen fugacity. So you get highly oxidized things and highly reduced things. You get a range of temperatures and pressures. Here, what dominates is olivine, pyroxene, plagioclase, nickel iron alloys, the iron sulfite trolite. What this is it's setting a stage for diversification again. And what happens after you accrete all this sand is that then you go through a whole period of metamorphic, aqueous, and igneous alteration, and also shock alteration that will diversify the chondrites. And one of the nice things about chondrites, especially if you're studying them under microscopes, is that the thin sections are beautiful. They often look like stained glass windows with in cross-polarized light. So I love looking at these things. So stage 2 is really a chondrite planetesimal alteration. You're altering essentially what you've accreted. And so chondrules accrete into planetesimals. Planetesimals accrete into planets. That happens over as much as 10 million years. Actually, it happens faster than that, but that's another whole class. Just note that it happens. We care about the results. The timing of the growth depends on location and local density of materials. And Steve Deutsch is going to talk about that in much more detail later. Heating becomes a critical factor. Now, there are 3 basic heat sources for planetary accretion. There's the gravitational potential energy from accretion, when you slam stuff together. There's the radioactive isotopes that I was talking about earlier. And also, when you get hot enough, if you differentiate, you actually release energy by having molten material fall to the core of an accreting planetesimal. Now, the nebula was seeded by the material from a nearby supernova. Things like aluminum-26, which has a short half-life, 700,000 years. That might not seem like very, very short, but remember that if you're talking about accretion of the planetesimals into planets over a few million years, you're talking about going through enough half-lives to essentially eliminate aluminum-26 before that period is over. And also, it's very abundant. Because of its abundance and short half-life, its heat generation potential is something like 1 million times greater than that of the uranium content of the terrestrial planets. So it's a huge input of heat early on. And so timing and size is key to the outcome in these heating, metamorphic, and igneous events. Planetesimals that accrete early, that is, they accrete with lots of aluminum-26, heat to melting and differentiate, and they produce igneous melts. But it's not going to take long before the isotope is depleted and the heating is only sufficient to metamorphose. As I said, Dr. Deutsch will be talking about planetesimal accretion and timing in detail. Basically, planetesimals that accrete outside the frost line are going to include volatiles as well as minerals. And remember, ice is a mineral. Heating of this assemblage is going to produce aqueous alteration. If you're inside the frost line, you don't have much ice, or you accrete later and never heat much, then you, excuse me, I went at that the wrong way. If you accrete outside the frost line, but you accrete much later than the aluminum-26 active period, you're not going to heat much. And so you're going to produce things like comets, which have unaltered high temperature minerals and ices sitting right next to each other. So the heating of anhydrous material, like ordinary and ancestite chondrites, produces new minerals by thermal metamorphism. And 950C is kind of an arbitrary number, but that's basically the start of the liquidus. That is the melting points for the iron assemblages that you have in these meteorites. You get things like phosphates, silicates like nepheline, oxides like rutile and quartz. And the thing with quartz is that you can have lots of versions of quartz depending upon the temperature. So quartz is relatively low temperature, but its high temperature polymorphs are the same chemistry, but a different crystal structure. And so you get cooked chondrites, things like dry lake, which is a high grade ordinary chondrite, and they're essentially very well cured in high heat. So a lot of these are very strong, very tough materials. For aqueous alteration, essentially you're melting ice and silicates at low temperatures. And then you get all sorts of new materials like montmorillonite, which is a sodium, calcium, aluminum, magnesium silicate hydroxide. And believe me, with a montmorillonite, you can get all of that in one collection. It's whatever junk is around. Chrysolite, kronstatite, oxides like magnetite and ferrohydrite. Again, the story here is almost all of these guys have water hydroxyl stuffed into their crystal structure. Sulfides, because you get a fair amount of sulfur, traulite, iron sulfur being changed into other things. Question?
When you melt these ices, what's happening with those volatiles? Is that...
Yeah, good question. Some of it goes into the crystal structure because there's no other way of getting the OH into the kronstatite other than just sucking it out of the water. And these things are small, they're porous, they're often highly fractured. So a lot of this will just move to the surface and sublimate off. So a lot of this gets lost to space. What remains, especially what's useful for resource, are the stuff that get locked in the crystal structures. Because once it's there, it's not going anyplace unless you do something to it. And of course, that's the whole point of an economic geology course, is doing something to it. Same story down the list. Carbonates, sulfates. Sulfates, of course, you're stuffing lots of water into these guys. So yeah, essentially what you're creating, like the CM carbonaceous chondrites shown here, are materials that are essentially 60 to 80% alteration products. And what's down here is the stuff that essentially survive the alteration. And if you look at these things under high magnification, what you see are lots of partially altered chondrules. That is, you've got an olivine chondrule that's being eaten, partially eaten into kronstatite or chrysolite or some sort of phyllosilicate. And this is a story that you see over and over in these guys. So on small near Earth asteroids, the only surviving volatiles are going to be in the phyllosilicates, in the mineral alteration products. As I said, aqueous processes on small asteroids are short-lived and tend to be open system. So water that doesn't go into minerals migrates to the surface, or sometimes it's retained in ice, depending on how well insulated these asteroids are. The largest main belt volatile-rich asteroids probably have a mantle of hydrated rocks with a crust of ice, salts, hydrated minerals. They might have salt-rich brines. So we just finished the mission orbiting Ceres, and we're still puzzled by a lot of the things we saw on Ceres. But it's quite reasonable to suggest that the mantle of Ceres is a quarter by weight water, and that it retains a lot of salt-rich brines, and certainly hydrated minerals, and probably ice. And of the 4 largest asteroids, 3 of them are probably hydration rich, and the other one, Vesta, is igneous and had been completely melted and differentiated. But these are big asteroids. We're not going to worry about big asteroids. Speaking of Ceres, speaking of Vesta, if the heating continues above 950, you go into the liquidus for early partial melts from nickel iron metals and trawlite. The sulfur and trawlite acts as a flux to reduce the melting point of the iron nickel agglomeration. And what happens is that the early melts migrate through the unmelted silicates because they're still, it's still not hot enough to melt any of that stuff. And you tend to form meteorites like Acapulcoites, Woonanites, 1AB irons. As you increase the temperature, then you start to form melts from pyroxene and plagioclase. Those go away, and the residual material after silicate melting, you get meteorite groups like uralites and lordonites. Question?
Jay Gren wants to know how thick are the crusts of the 4 large asteroids?
That is an excellent question. I don't know offhand. I vaguely remember some numbers, but I would hazard to give you an exact answer. And some of the crustal thickness estimates are highly controversial. So I will punt on that question and say something I often say, which is I don't know. So the partial melts also sequester, that is, they leave behind a range of incompatible elements, like phosphorus, sulfur, carbon. And they react with the unmelted silicates to form new minerals. The point is that this is one mechanism where you can concentrate relatively scarce elements and react them into new forms. And that's really the key in mineral evolution is being able to concentrate in new chemical and physical environments. Yeah.
Conrad has a question. He said, does the formation process of the 4 largest asteroids affect their current shape?
The short answer is yes. But that's again another area that I don't know nor or understand very well. So I'd have to defer to others for that. Just to remind you, all of these elements have chemical proclivities. They have they prefer certain other types of elements, and so siderophile and chalcophile elements tend to migrate to cores. Lithophile elements react and make make more rocks. Amphibole elements are either in gases or volatile species, and just keep that in mind. And so when you're into igneous alteration at high degrees of melting, what you do is you're going to sequester siderophiles from lithophiles. The siderophiles are going to move down to the core, and they're going to crystallize separate. All this stuff is going to crystallize separately to form the core, the mantle, and the crust. With the crust, you're going to concentrate incompatible elements. This is where you get lots of potassium and aluminum, and calcium, and stuff, and zircons, badentonite. I love that name for a mineral. But this is a process that we'll see a lot of in asteroid and lunar geology. This concentration of incompatible elements. At the core, the mineralogical diversity is driven by fractional crystallization and solid state transformations during cooling. And so you get a lot of things. This is what drives this rather gorgeous pattern in iron meteorites, the Widmanstätten pattern. It really shows you the crystallization of nickel-rich and nickel-poor areas within this iron-nickel melt of material. And what happens is that these things get sequestered during cooling. Also, the little blob here, that's more trollite, which is iron sulfur. So the other factor to remember is impacts. Impacts are ubiquitous, and really that's been the action in asteroids for the past 4.5 billion years. And so you form shock minerals. Now the high pressure minerals are often polymorphs of lower pressure common minerals. So olivine goes to ringwoodite. When you melt chondrules or base chondrule compositions, you can get garnets. You can get magnetowustite. Enstatite goes to achimotite. Plagioclase feldspar goes to mescalinite. This was, and there's many, many more. And for asteroids, what happens is they get rubbleized, particularly in the asteroids in nearest space are collisional fragments and rubble piles. In larger bodies, you get the excavation of deep igneous or metamorphic terrains. And if those are volatile rich, that can initiate hydrothermal activity. There's a whole issue on Earth with a number of big impacts initiating hydrothermal activity. You also get deep subsurface hydrothermal zones if there's water, like on Mars. So, heat drives mineral evolution. But on asteroids, since they're small, heat from accretion core formation and radioactive sources died pretty early. This is the timeline in the diagram of time after calcium aluminum inclusion formation. And it goes out to 100 million years. But basically, for asteroids and planetesimals, even big ones, you're done after about 20 or 30 million years, even for thermal metamorphism and things that totally differentiated, like the eucrites. After this period, the only activity, the only action in mineralization is going to be impact related. And between the original mineralogy, the aqueous alteration, the metamorphic alteration, the impacts, and the igneous evolution, after all of this, you get 250 minerals. Question?
When you're trying to understand how something like impacts forms, like one mineral turns it into another, is this something that you observe on the asteroid, like when you get a sample, or are we in the lab like colliding things?
Well, the short answer is both.
Okay.
Typically what, this is driven by observing in detail mineralogy of meteorites. And remember, we have 70,000 of them to look at. So one of the things that, one of the features of the meteoritic profession over the last 20 years is we are discovering meteorites far faster than we can actually even catalog them, much less carefully study them. We go down to, National Science Foundation has these great expeditions down to Antarctica every year. Every year they find between, a few hundred or more meteorites, new meteorites to add to this collection. So, and then people are scavenging the deserts and the dry deserts in North Africa and Australia are just huge bonanzas for finding meteorites. So we're finding them faster than we can characterize them. And there's plenty of data there to be mined. But just an aside. So stage 3. Stage 2, we're done with the meteorites. No more evolution. The moon gets into stage 3. And of course, as I said before, the moon is a product of what is likely a giant impact between the Earth and a Mars-sized planetesimal. The impact ripped, since both of these planets were already differentiated, the impact ripped off the crust and mantle. And the crust and mantle were what you got to form the moon from. But that meant that you already started with a material that was already depleted in hydrophile elements. Since this was a very high temperature collision, volatiles would have been vaporized. And of course, the accretional energy liberated during reaccretion would essentially heat the material that you're accreting into the moon into a magma. And so you get a magma ocean. The next 3 or 4 lectures are going to talk a whole lot more about the geology and the evolution of the moon. I'm going to stick to the implication for mineral evolution. So hot accretion meant that most or even all of the moon was initially molten, probably just most. And the magma ocean cooled actually more slowly than it otherwise would because you were still inputting energy from tidal dissipation. The moon had probably accreted vastly closer than it is right now. And so tidal coupling with the Earth would transfer Earth's rotational energy into the moon and keep it relatively warm. So the magma ocean differentiated. The dense stuff, the olivines and the pyroxenes, as they crystallize, would drop to the bottom of the ocean, and the less dense, more felsic stuff, the anorthite, would float. Just like in the igneous asteroids, as you get into high degrees of crystallization, you concentrate the incompatible elements, and you tend to concentrate them at the base of the crust. And this is where you get the so-called creep terrains, potassium, rare earths, and phosphorus, that we see in the Procolarum Basin. And so also, just like in the igneous asteroids, you get mineralogical diversity from both fractional crystallization and solid state transformations during cooling. And so the creep terrain is concentrated in the base of, in the Procolarum and Imbrium. And the stuff is there basically because this is a source region for subsequent basalts. Oddly enough, because they're incompatible, things like thorium, you end up with a large proportion of the moon's inventory of heat-producing elements, of radioactive elements, incorporated into the creep. And what happens is that during 4.2 to about 3.2 billion years, you produce the Mare terrains that we see on the lunar near side. And these basalts are going to be coming from source regions that tap this creep material. And so these things get enriched in the basalts and end up on the surface. One of the reasons why the basalts on the moon are so liquid and look like oceans is that because you basically have a total absence of water, water acts as a flux to lower melting points on terrestrial melts. And so in order to get a melt, you have to go much hotter. And as a result, you erupt much hotter and much more fluid than terrestrial basalts. So basically all rocky planets and moons have gotten through stage 3. And even volatile poor bodies like Mercury and the moon, this process is going to give you about 350 minerals. If you get water or other volatiles, you'll get an enhancement in hydroxides, hydrates, carbonates, evaporates, and you get about a total of about 500. So Mars probably has at least progressed that far in mineral evolution. Mercury is probably about at the 350 stage. So that brings us to the bottom of stage 3, igneous rock evolution. And those are the planetary, the planetary results for mineral evolution. Just to run you through what you don't see in lunar and asteroid geology, I will briefly go over the other stages. Stage 4 is you have enough heat to remelt the initial basaltic crust. So you form granitoids. Things like pegmatites, which I'm not going to get into, but the thing is that you concentrate relatively rare elements to make a bunch of distinctive minerals. Stage 5 is the onset of plate tectonics, because since we are water rich, that lubricates and allows for plate tectonics. And then what you're doing is shoving water-rich crustal materials back into the crust and mantle. And you get a huge range of fluid rock interactions and rare element concentrations. And that cranks up 500 more minerals. You start getting an anoxic biosphere that interacts with the lithosphere and primitive microbes. And really, the advent of bugs is a huge catalyst for mineral development. And so you get up to 1,500 mineral species. And probably any volatile-rich anoxic terrestrial planet will have about that many. The big difference with Earth is the great oxidation event. The rise of atmospheric oxygen more than doubled the amount of mineral diversity you have on this planet because of the oxidized, hydrated, and weathering products that you get from other minerals. And basically you rusted the planet. You started out with black basalt and ended up with a planet that looked a lot like Mars does these days and turned red because you're taking ferrous iron and turning it into hematite. And this is where you got most of the iron ore on the Earth in the banded iron formations because you're oxidizing the free iron that's still sitting around on the surface. Stage 8 and 9. Stage 8 is basically the boring billion. This is a billion years where not very much happened. Stage 9, you get fluctuations in climate and atmospheric chemistry that created snowball Earth events. Glaciation enhanced weathering and produced all sorts of sulfides and clays. And then the final stage is when you have the creation of minerals by living organisms in a widespread fashion. buildup of atmospheric oxygen allowed plants to colonize the surface. And when you start having plants on rock surfaces, that allows for really rapid breakdown of rock. And so you hugely increase weathering rates and the abundance of clay minerals, and increase the rate and formation of soils vastly. So, to wrap up, mineral evolution are fundamentally different on moon and asteroids versus the Earth. You get about 250 minerals on these evolved asteroids. The moon has some more, 350. The geological concentration mechanisms that we depend on for terrestrially for ores don't exist on the moon and asteroids. So on asteroids, no high heat flow, no available fluids, no hydrothermal systems for the last 4.5 billion years. Your last hydrothermal system was this modest aqueous alteration we get in carbonaceous chondrites. That was over a long time ago. On the moon, no fluids or hydrothermal systems. What you get is Mare volcanism tapping creep source regions for enhanced and incompatible elements on the surface in some of the basins. Impacts and shock, that's what you get today. That's what we've gotten for the last 3 billion years on the moon and 4.5 billion years on asteroids. So thank you very much. And I will call for questions. So questions around the table, particularly from those who haven't asked questions before. And keep a look at the text box for questions.
So do we find any minerals on any of these other bodies that are not on Earth?
Any minerals that are not on Earth in these other bodies?
Yeah, because I know like Mercury has very interesting chemistry.
Yeah, Mercury does have very interesting chemistry, but I'm not sure of the answer. There might be some rare pressure and fugacity conditions that produce relatively rare minerals that you don't find on Earth, but go ahead and leave that on for everybody else. They're certainly not abundant. Yes.
From the chat box, Dennis wants you to know this is brilliant stuff, and Isabel would like to know if you could please elaborate on what an anoxic biosphere consists of.
An anoxic biosphere is one that is not oxidized. Why did I say that? But basically, it's reducing conditions. So an anoxic conditions are things that allow you not to weather or break down carbon compounds. So the reason we have oil reservoirs is oil forms in anoxic conditions. Yes.
Okay. I was unclear, but what are pseudophiles and mesophiles?
So pseudophiles are elements that like iron. And so when iron is in motion, so you melt iron, those elements go with the iron. Lithophiles are rock-loving elements, and so those are the ones that form into crusts and mantles. The pseudophiles form into cores, and the chalcophiles, they mostly go with the pseudophiles, but they hang out with the chalcophiles too.
So when you say incompatible, does that mean they don't love anything?
That's right. These are people that just don't get them. Incompatibles are things that don't fit well into crystal structures.
Okay. Because they're weird shapes or
because they're weird sizes.
Okay.
So if you look at the atomic radius of most of the things I talked about as incompatibles, they're just big. And crystal structures only have specific sizes that'll fit in that will fit certain atoms in those crystal structures. So olivine, for instance, has a couple of sites that you can fit atoms in, given by the structure of the silicon and oxygen. And basically the only thing that's of any abundance that will fit there is iron and magnesium, because their atomic radius at that oxidation state is about the same. And that really drives all the mineral formation is whether you have a crystal, a zone in the crystal where you can fit an atom. And a lot of these atoms will substitute for each other. For instance, strontium substitutes just fine for calcium. In all of these minerals, it's just strontium is not very abundant. But the reason radioactive strontium is so deadly is that your bones love strontium just as much as they love calcium. And so that's where it goes. And that would be bad. Yeah.
I know you talked a lot about Mars and how far it made in the stages. Do we know a lot about how far Venus might have made it, because it's like the sister Earth?
Well, it will make it. It made it probably into the next stage, into remelting of the salty crust. Undoubtedly, it made it that far.
Okay.
But to get any farther, you need volatiles.
Right.
And that's a big problem, because the volatiles, the hydrosphere and hydrothermal action produce a lot of that action. So, yes, farther, but not that much farther. However, if we ever get to the surface of Venus, we'll probably learn a whole lot more about that process and maybe get surprised. Because remember, the whole point of this exercise is to discover new things that we haven't thought of already. Yeah.
There's some chat questions. Jay Gruner would like to know, do we see any evidence of phyllosilicates at the lunar poles that may be due to rock-ice interaction?
Not that I know of. Kevin Cannon is going to talk about the mineralogy that we'd expect and observe at the lunar poles, but I don't know of any.
Hypothesized but not observed.
Kevin says it's been hypothesized but not observed.
Ryan Kreiser said, I read somewhere that ringwoodite contains more H2O than all of the surface water on the Earth. Is that true? If so, can we extract H2O from ringwoodite on other terrestrial bodies and planets? How complex would that process be?
The short answer is yes and no. The reason ringwoodite contains a lot of water, but it's a high pressure polymorph. And it's very abundant in the crust, or in the mantle, excuse me, because it's a high pressure mineral. You're not going to get any of that, you're not going to get those kind of pressures on asteroids at all. So that's not, and actually getting to it to extract water, it would have to be at great depth. And so it would be really tough, even in a planet the size, analogous to Earth, to ever get at ringwoodite. So I would not think that it's a very attractive prospect.
Okay, David Carl asks, during the moon's formation, where are the minerals from the Mars-sized planetoid, and where was this body formed in our solar system?
Good question. There are lots of discussion about this. The short answer is because of the looking at the isotopic systems on the Earth versus the Moon, probably this Mars-sized impactor formed more or less in the same space as Earth, and out of the more or less the same material. So it was very similar to Earth to begin with, and basically the impact created a debris disk which thoroughly mixed the ejecta from both the impactor and the target, so the Earth and the Mars-sized impactor. So when they accreted, they were thoroughly mixed. They accreted hot, so most of it melted. And so you just don't see residual material because all of this stuff got as thoroughly mixed as possible. And the isotopic systems where you would see that kind of residual material started out being very, very similar. So probably this thing was co-orbiting with the Earth for a long time, long being a few 100 million years maybe, before probabilities caught up with you and it whacked into the Earth.
Okay, Jay Gruner wonders, how common is masculinite?
How common is masculinite? It's actually quite common in felspar-rich impact environments. And one of the places that you see it a lot is in Martian meteorites. So it's probably one of the more common impact polymorph, high pressure impact related polymorphs that you find in mineralogy.
Okay, and they said particularly in Apollo 16.
Yeah, and
Okay.
also, yeah. You also find it on the moon, wherever you find feldspar. So if you're going to Lunar Highlands, for instance, you'll probably find a whole pile of mescalinite. Any more? Yeah.
So one of the things in carbonaceous chondrites is kerogen, and kerogen is like an amorphous carbon thing. It's commonly known as coal shale on Earth. It's not a crystal though, so what would you classify it as?
Mineraloid.
Mineraloid, okay.
Yeah, kerogen, the organics in meteorites are not really the subject of this lecture because I don't do anything that was living or could be living. No, well, actually, in all seriousness, the evolution of these organics is a whole nother and way more complex system that I leave for other people because it's too hard for me. But yeah, you're very right that you have a bunch of carbon compounds in carbonaceous chondrites. And the amount of carbon compounds are strongly related to their level of aqueous alteration and the amount of water that's retained in the crystal structure. So with water-rich carbonaceous chondrites, they're very rich in these carbon compounds. And they can be mind-bendingly complex. More questions? Well, go ahead.
Sorry, Dennis Trevino says, specific to Mars, are there worries similar to the moon of small particles migrating into controlled biospheres?
Yes. The problem is that all of these environments grind up the surface regolith very fine. So if you're trying to control your environment, you're going to have a dust problem all the time. And the dust is likely to be highly reactive and with very complex and rough shapes. So it would be bad. Yeah.
Continuing on this Mars side, is there sedimentary rock on Mars? And if so, is it still being made at all?
Short answer is yes, lots.
Mm-hmm.
And I don't know how much, well, you're getting aeolian deposition, that is wind-driven deposition all the time. That's a sedimentary material. And so, yes, that goes on. You don't have liquid water on the surface right now, but you have glacial action also. So there's a lot of sedimentary processes that can still go on even in a rarefied atmosphere.
Because I'm assuming sedimentary processes are the main thing that gets rid of small dust-like particles on the surface.
Well, yes and no.
Okay.
Sedimentary sedimentary activity can stick them together. They can also various drivers of sedimentary processes can rip things apart. So wind can actually abrade and produce dust. Glaciers are a great way of producing dust. So on Earth, the high glacial periods were actually hugely dusty relative to what we are today. So you drive to Iowa and Nebraska, and you find sedimentary deposited dust layers that are tens of meters thick from glacial epochs. Yeah, it both generates and deposits dust. So I would think the net effect is to produce more dust over time.
Well, then why isn't the surface of Earth covered in dust? Is it plants?
Well, the Earth is covered in plants.
Okay.
And plants are great ways of fixing dust. More questions? Okay, well, thank you all for joining me here, and we'll be back on Wednesday for a discussion of this. And I hope the online audience feels free to join us in the discussion. Okay, thank you very much.